Cool cats and kittens, welcome back to engineering physics. Here's the second section on thermodynamics. Okay, so just defining some basic terms here. Throughout your science career, you've heard the terms open system, closed system, isolated system. Well, to define the word system, we've talked about this before, I think probably mostly in chemistry class, but system is basically a fancy way of saying the thing you're talking about. So wherever you draw your boundary around something like a calorimeter or something like that, that could be your system. So for example here, if you could define a beaker to be the system, and then stuff inside the box, that's the surroundings. Or you could then, it doesn't matter where you draw your boundary in terms of you draw your boundary bigger and bigger and bigger and bigger, you're talking about, you could have the whole universe be your system. So essentially for this, we're going to be talking about an ideal gas, same thing we were talking about in chemistry 20. And as you remember, ideal gas law, the model is the particles of the gas do not exert intermolecular forces on one another. They don't change state when they cool down. They don't liquefy, and the solid doesn't solidify either. So the internal energy of a gas is only due to the random kinetic energy of the gas particles, or the molecules in this case. So here is a formula to determine the amount of internal energy of a gas. The only variable there is temperature in Kelvin. So, and also the chemical amount as well. So chemical amount, ideal gas constant, and temperature. So kind of makes sense. More temperature, the increase in the higher the temperature, the more internal kinetic energy you've got. All right. So I stumbled through that first slide. See if we can get through the second one. First law of thermodynamics, essentially the law of conservation of energy as applied to thermodynamic systems. So this equation here is one that we're going to be using for the whole rest of this section. So going to be constantly referring to it. So Q, sort of like Q equals mc delta T, is amount of thermal energy. So if Q increases, gas, again, our ideal gas gains thermal energy. If it decreases, loses thermal energy. So very similar to what we were talking about before, endothermic, exothermic processes, stuff like that. Internal energy, again, applies to a change in temperature. So if it goes up, then that means an increase in temperature. If it goes down, that means a decrease in temperature. And then work. So work done either on the surroundings by the gas. So if the gas expands, essentially, if you have a piston like on a container of gas, and when the gas expands, that piston goes up and then it does work on the surroundings. Whereas if the gas decreases in volume or compresses, then the surroundings has done work on the gas because the atmospheric pressure pushes down on that plunger, what we're talking about for a sample of gas. Okay, so three quantities: pressure, volume, and temperature, we can use to describe the state of a gas. So we learned about Boyle's law, Charles' law, all that kind of stuff, where pressure, volume, temperature, they're all related to each other. So instead of what we would need to represent a change in all three variables, pressure, volume, and temperature, we'd need an X, Y, and Z axis. Pressure, volume, temperature. We could use those, but those are kind of hard to draw, so we don't. We use what is called a PV diagram, where you've got pressure on the y-axis and you've got volume on the x-axis, and then as you move from one of these lines to another line, which we'll get to, you're changing temperature. So these lines right here are curves, and they're called isotherms or isothermal lines. So anything along this, an isothermal line represents a constant temperature. So notice these pressure and volume relationships are consistent from what we've seen before with Boyle's law. As the volume of a gas increases, the pressure of the gas decreases. Kind of makes sense. Changing temperature here would be of a low temperature, and then you move from isotherm to isotherm to isotherm. You've got higher and higher temperatures. Okay, so there's a few different types of changes that a gas or our system, our ideal gas, will undergo. First type will be called isobaric, and if you remember from like the news, if you're listening to the weather, they talk about the barometric temperature or the barometric pressure. I mean, not temperature, barometric pressure, and you use a barometer to measure pressure, or pressure. So if it's isobaric, it means constant pressure. So pressure of a gas remains the same. So an isobaric change in one is in which you've got a constant pressure. Isobaric changes occur when gases are allowed to expand or contract freely. So let's say you heat up a gas, for example, it's going to expand, but in order for the pressure to stay the same, the volume has to be able to increase. So the work can be done by the gas. So again, when you push a piston out as a result of heating this gas, work is done on the system. Or if you cool a gas down, for example, the gas will compress, and then your plunger will come down again, and you've got work being done by the system on the gas. If you're talking about a PV diagram, in going from there to there, sort of from point A to point B right there, notice what happens. We're moving from one temperature to another, because we're going from one isotherm to another isotherm. And also the volume is shown to be increasing. So this would represent a change of heating up a gas, where the pressure remains constant. Notice if you draw a line from A to B here, you've got a horizontal line. The pressure does not go up or down. That's because the volume is allowed to increase. That plunger is allowed to go up. The volume gets bigger as the temperature increases there. When you've got an isobaric change, again like this, constant pressure, when you want to figure out the work done, in this case the gas expanding, the work done on the surroundings by the gas, it is equal to the area under the curve. So pressure, so area equals length times width. So here you've got a rectangle, pressure times change in volume. That's all that is. And going back to our statement of the law of conservation of energy, the first law of thermodynamics, this work done, you can write it as P delta V here. So you'll see in your word problems that here we've got 1, 2, 3, 4 variables. You'll be given 3 of them and asked to solve for the 4th. The work done for non-isobaric changes is also area under the curve. So it doesn't really matter if the pressure stays the same. Like here we just made the pressure stay the same because it's easy to find the area under that shape, right? We've got a rectangle. But let's say you've got a change where you go from here to there. So this is an example of what we'll get to, a change at a constant temperature. So if you remember that if the pressure stays the same, that's called isobaric. If the temperature stays the same, it's called isothermal. But we want to find the area under this curve. Well, in order to do that, we have to, well, if you don't have calculus here, remember calculus, you draw a bunch of rectangles, find the area under smaller and smaller rectangles, and you eventually get the area under the curve. You have to do an approximation. So what we would normally do is draw ourselves a little triangle from there to kind of represent this top part here as kind of a triangle. It's an estimation, and then we've had a rectangle on the bottom here as well. Okay, isothermal. So notice that was an isothermal change where it was along one isotherm. This is what we're getting to next. Starting from there to there. So notice the temperature stays the same, but we can just read the graph. The pressure goes down and the volume goes up. So an isothermal change is a very slow process where there's no change in internal energy. So this Remember, this delta U is that internal kinetic energy. If the temperature stays the same, that does not change. So that means then, if in our statement of law of conservation of energy, the first law of thermodynamics, if this delta U term, which depends on the temperature, stays constant because you got a constant temperature, that means that change in internal energy is zero. Therefore, the increase or decrease, in this case, of thermal energy is equal to the work done on the surroundings or by the surroundings. It depends which way you're going. So this is an isothermal expansion. Expansion going from B to A, because we notice that the volume is increasing. So all the work done on the gas or by the gas on the surroundings is supplied by the internal thermal energy transferred into the gas. And an isothermal compression, if you're going from A to B, we notice the volume is going down, but the pressure is going up. The work done on the gas is all transferred away from the gas as thermal energy. So restating that same thing. So for an isothermal change, you've got pressure and volume being a constant. That just Boyle's law. So you learn about Boyle's law in Chemistry 20. We reviewed it back when we did gases at the beginning of this course, but we didn't call it an isothermal change. So the temperature stays the same, and you've got, if the pressure goes up, the volume goes down, and vice versa. Okay, so I think this is the last one we're going to go through. Adiabatic, whatever, potato. Let's go adiabatic. So for an adiabatic change, notice what's happening. I'm not going to read this text here, but we'll take a look at this. We notice the pressure changes, obviously, because you've got a rise here. The pressure goes down, the volume goes up, and also the temperature changes as well. You start off at a higher temperature and you go to a lower temperature. So in this type of change, there is no thermal energy transferred between the gas and its surroundings. So for a process to approximate the ideal of being adiabatic, the change must be very rapid and in a very well-insulated container. So for that, you've got 0 for an increase or decrease in thermal energy. So in an adiabatic expansion, all the work done by the gas is transferred from the internal energy within the gas, and the temperature then goes down. So notice we've got a negative sign for delta U here. And the negative sign means that the internal energy, the thermal energy, no, it's internal energy, all right? Let's go back. Internal energy, yeah, the internal energy goes down. Therefore, it's expanding. It loses energy. If the internal energy goes down, it must then give off energy to the surroundings, and that's an expansion. That W is then positive. In a compression, if you go the other way, the rapidly expanding piston hits the gas molecules, giving them kinetic energy, and then the gas gets hotter. So here we've got a compression. So you're slamming down on that piston, and the work done by the surroundings on the gas increases. That slams into the particles of the gas and then gives them kinetic energy and causes them to move faster, thus increasing the total internal kinetic energy there. Okay, so for an and I keep mispronouncing it, adiabatic change of an ideal monoatomic gas, you've got, this is how exactly it appears in your data booklet, pressure times volume to the power of 5/3 is a constant. So we're not going to get into the derivation of why is it 5/3. It's not necessary for this particular part of the course. Okay, last one, isovolumetric. So the volume does not change. So you've got let's say a container where the piston doesn't have a piston. It does not move up or down. It is a rigid, say, gas container or something like that. So no work done by or on the gas. So again, If you expand, work is done by the gas on the surroundings. If you contract, then work is done on the gas by the surroundings. But if you've got a constant volume, isovolumetric, there is no expansion or contraction. So your work value here done on the gas or to the gas by the surroundings is 0. So that means thermal energy is transferred into or out of the gas. The temperature of the gas simply goes up or down. The volume does not change. And remember, that's essentially Charles' law, the relationship between pressure and temperature. Okay, so where this applies in engineering is in the Carnot cycle, cycles and engines. Here we go. So in a heat engine, you've got the transfer of thermal energy causing expansion, while useful mechanical energy is done by the gas. So an internal combustion engine, you burn the gas expands, and then you pushes a piston, and then you've got that motion. So obviously you'd have a terrible engine if that just happened once and your piston expanded and then that's it. That's your engine, your car stops. It has to be a cyclic process. So the gas has to be compressed again, returned to its original state, and then expanded, and then compressed, and then expanded, and compressed, and expanded, and compressed, and then you get that constant motion. So the thermodynamic cycle that produces that maximum efficiency that you want in an ideal gas is called the Carnot cycle. And it consists of this. It consists of a isothermal expansion, an adiabatic expansion, so the volume is going up, and then an isothermal compression, and then an adiabatic compression. So there's your ideal thermodynamic cycle. So again, the area enclosed is equal to the net work done by the gas on the surroundings in one cycle. So one of your word problems you're going to have to do is approximate the area of a shape like this. So essentially it's going to be like the area under this big shape right here, and subtract this little area down here and give you this area over here. I really would want you to click on this link here to take a look at a detailed explanation of the Carnot cycle. In general, the thermal efficiency, represented by lowercase n, of any process is defined as, well, this is probably pretty easy in Science 10, whatever, when we first learned this, we just put EFF for efficiency, but it's basically output divided by input, useful work done divided by the energy you put in. This is one of those things in an IB physics course where you just like, unfortunately, give you a formula, here it is, go use it kind of a thing. So the following equation can be used to calculate a maximum possible efficiency within a Carnot cycle right here, where you're given two temperatures and you're able to determine the efficiency of a Carnot cycle based on the difference between two temperatures. Okay, second law of thermodynamics. Essentially, you guys learned about this in Science 10. We learned about it where thermal energy always travels or goes from an area or a substance at high temperature to a substance at low temperature. So we can express it actually in three ways here. The Clausius version, this is what you learned about in Science 10, what I just finished talking about. Thermal energy cannot spontaneously transfer from a region of lower temperature to a region of higher temperature. In order to do that, you need to do work. And you guys learned about heat pumps and stuff like that in Science 10. We didn't call it the Clausius version, we just called it the second law of thermodynamics. A couple more. The Kelvin-Planck version. When extracting energy from a heat reservoir, it is impossible to convert it all into work. So basically what that means is any energy transformation, you're always going to lose heat energy. You can't possibly get 100% efficiency transfer in terms of one form of energy to another form of energy. You could also write that as a consequence of entropy, which we'll talk about in a sec. So in every process, the total entropy of an isolated system or the universe as a whole always increases. And that's the last thing we're going to talk about, is what is meant by entropy. And entropy is essentially randomness. It's a numerical value that expresses the disorder of a system. So here I have a little thing for the smartboard. Consider the 3 diagrams which would show the distribution of the same number of gas molecules in a container and order them in the most likely sequence. So would you have number of molecules on both sides of a dividing line equal at the start, and then all of a sudden they would just spontaneously move to one side? The answer is no, you wouldn't. Your natural process would be kind of like diffusion. You guys learned about in Science 10. You would start off with an area of high concentration, an area of low concentration. You would have the particles spreading out, and then eventually they would come to equilibrium on both sides of the membrane here, or whatever we've got. So that would be our increase in entropy or randomness. So, like it says there, the concept of entropy numerically expresses the disorder of a system. So it's assigning a number to the disorder. So when an amount of thermal energy, delta Q, is added to or removed from a system at temperature T, the change in entropy, delta S, can be calculated as the change in thermal energy divided by the temperature. And again, entropy is kind of a weird kind of concept to wrap your head around. Entropy means randomness, so how do you assign a number to randomness? But again, just for this little brief explanation through the notes, it is recommended that you follow the links that I will insert below, and then in your Google Classroom assignment, learn a little bit more about that. If you're even more interested in it, I highly recommend that you do the following. You read pages 559 to page 569, and then attached will be your handout that you can practice on thermodynamics. Okay, well, that's it for today. See you guys later.